Experiments in Physics with Dr. Frank, a brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment
in this experiment, one can measure acceleration with this accelerometer. Measure acceleration such as omega squared r on this rotating table, and understand the action of the accelerometer. One can also use the accelerometer for other things. For example, you can simply try walking with it and seeing if you can, even horizontally, you can keep any accelerations away. This has something to do with carrying teacups full of tea. I presume one could use it to measure accelerations on anything in which you could mount this, on various carts, or even perhaps on a pair of air troughs. Let's look at the accelerometer. It consists of a heavy mass here, a brass mass mounted on a fairly light aluminum frame. This provides the inertia, which when I accelerate it moves it. There's a pointer and a scale which can be used quantitatively to measure the acceleration, and the restoring force is provided by these two springs which are set to have it in the center. In addition to that, the accelerometer can tip. There's a clamp there and a protractor, so one can measure the angle at which it's tipped. There are very light, very delicate bearings at these four corners, and one of the important things to do is not to drop this accelerometer. That's not an idle injunction. You can see by looking at these corners it's been dropped, and we have to put in new bearings every once in a while, and often don't catch up with the thing before people try to do experiments with it. So do be careful of it and consider it a delicate instrument, even though it doesn't look like one. In order to see how to calibrate this, we have an auxiliary experiment in which we use an accelerometer with wheels on it. Here it is. It's the same as the other one, except it has wheels. And first one should check the wheels and see that they spin. Actually, this one is dragging a little bit now and needs washing out with acetone, but otherwise they spin quite well. Then one should set this on a level table, and I believe that this is leveled now. I've just checked it. Yes, and one can set the accelerometer so that this upper part is level 2, and there's a stop there adjusted by this little Allen red wrench here and a screw, so that one can adjust the level so that when it's sitting on a level table, the bubble level is exactly in the center, and that then will give you the 0 reading of the accelerometer, which is now just about 9 divisions on the scale. And now we can take this accelerometer and put it on an inclined plane, which is shown here, which is over here now. And clearly, the thing is tipped down. The more I tip it, the further down it goes. And then I can let it go and let it roll down the plane. Well, when it does that, it shakes a little bit too much. I may have, if one wheel drags more than the other, I may have to start it off a little to compensate that. It was shaking so much I couldn't read it exactly, but I saw about where the pointer was, and this time I'll hold the pointer there when I release it. And there's very little shaking, and I can read quite accurately to about 1 millimeter where the pointer is. And it didn't quite come back to its original position because there's a little friction, but it almost did. In addition to that, I can also, for example, raise the accelerometer. I guess I'll have to turn it around to do that, till it reads level here, rather than having tipped it, and measure the deflection. It now is not now at reading right at 0, and I'll let it go down. Again, I'll have to start it so that it doesn't shake too much. And read what the deflection was and see that it's the same as the deflection when it was tipped through that same angle. In other words, I can convince myself that by measuring this angle and calculating the acceleration by g sine theta, that this device is measuring that same acceleration. Having done that, I can then calibrate this wheelless accelerometer using this protractor. That is, here's the protractor. There it was. I'll first get it level, and then read the protractor, then tip it up, say 2 degrees at a time, clamp it, and read the deflection, and make a graph of the reading on the scale versus g sine theta expressed in meters per second squared, and in that way I can get the scale calibrated in meters per second squared acceleration. Having done that, I can then use it quantitatively. Before I use it on this table, I want to make sure that the table is level. In order to do that, I'll use this, release the drive here by pushing this wheel in and turning it a little till it locks. Let's look at that a little more closely. Just for a moment. Now it's turning when I push this in, like that. It gets in behind there, and then I turn it a little more, and it's locked behind. Then this will turn freely. And now I'll set this so that it's level, and look down on the top, and you can see, perhaps can't see it now, but the bubble is level there. I'll turn it a little bit and make sure it's still level. And if it isn't in this direction, I'll use these screws which are underneath here to level it a little. It's a little high on one side, so I'll center it. And now try it all around. I probably should have this on here at the same time to make sure that the axle isn't bending as it goes around. And now I can level this as it goes around. And these, if it's level here, yes, so it's all right. I may want to move these around a little bit to keep any bending out of the axle. And now it's staying level in any position I put it. So the table is adjusted, and I'll release this simply by turning it till it gets against the disc again, and I can now measure accelerations. First, I can measure, for example, radial accelerations by putting this along the center of mass here, right along, so that the motion is right parallel to a radius, and start this up. I don't want to have it moving too fast, or the whole thing would slide off, but I get an appreciable deflection here. I can read what that is. It's about 2.25 centimeters. And then I can measure the period of that by starting at 1 and so on till I know the period, and from that I can get either the velocity or the frequency. In order to measure the radius, of course, I'll have to measure the radius to the center of mass. So having read that, which is now about 4 divisions, I can just take a ruler and measure not to where it is when it's sitting still, but measure to where it was when it was out, and that gives me the radius from the center here to where the pointer was when it was moving, gives me the radius of the motion. If I want to try it at a different speed then, or a different radius, I can move it out and do it again. And I can vary the speed. Of course, I can only use it up to speeds in which I get that's about as fast as it can go at that radius and still have the deflection on scale. In addition to radial accelerations, I can measure any component of the acceleration, in particular the tangential acceleration. For example, I can put this so that it's tangent to the circle through here and start it up. And of course I get an initial one, but it'll eventually settle down, and then I can read what the tangential acceleration is at various speeds and positions. And that's all that's involved in this experiment. Again, let me caution you to be careful of the accelerometer and to think of a variety of things to do with it, even though they may not be mentioned in the write-up.
Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television. This is University of Colorado Television.